Section 3.3 Formula Weights. Chemical formulas and chemical equations both have quantitative significance in the subscripts in formulas, and the coefficients in equations represent precise quantities. The formula H2O indicates that the molecule of this substance, water, contains exactly 2 atoms of hydrogen and 1 atom of oxygen. Similarly, the coefficients in a balanced chemical equation indicate the relative quantities of reactants and products. But how do we relate the numbers of atoms or molecules in the amounts we measure in the laboratory? Although we cannot directly count atoms or molecules, we can indirectly determine their number if we know their masses. Therefore, we can pursue the quantitative aspects of chemical formulas and equations. We must examine the masses of atoms and molecules. Formula and molecular weights. The formula weight of a substance is the sum of the atomic weights of the atoms in the chemical formula of the substance. Using atomic weights, we find, for example, that the formula weight for sulfuric acid, H2SO4, is 98.1 AMU. The formula weight of H2SO4 is 2 atomic weights of hydrogen plus 1 atomic weight of sulfur plus 4 atomic weights of oxygen. So the atomic weight of hydrogen is 1, so 2 times 1. Atomic weight of sulfur is 32.1, so that's 32.1 added. And 4 times the atomic weight of oxygen, which is 4 times 16, add that together is 98.1. For convenience, we've rounded off the atomic weights to 1 decimal place, a practice we'll follow in most calculations in this book. If the chemical formula is the chemical symbol of an element, such as sodium, the formula weight equals the atomic weight of the element, in this case 23.0 AMU. If the chemical formula is that of a molecule, the formula weight is that of the molecular weight. The molecular weight of glucose, for example, is C6, so 6 times the atomic weight of carbon, so 6 times 12, H12, 12 times the atomic weight of hydrogen, so 12 times 1, and O6, 6 times the atomic weight of oxygen, so 6 times 16. Added together is 180 AMU. It's the molecular weight. Because ionic substances exist in 3-dimensional arrays of ions, it is inappropriate to speak of molecules of these substances. Instead, we speak of formula units. The formula unit of sodium chloride, for instance, consists of 1 sodium ion and 1 chloride ion. Thus, the formula weight of NaCl is defined as the mass of 1 formula unit. The formula unit of sodium chloride is 23 AMUs because of 1 sodium, and 35.5 AMUs because of 1 chloride. Added together is 58.5 AMUs. Percentage composition from chemical formulas. Chemists must sometimes calculate the percentage composition of a compound. That is, the percentage by mass contributed by each element in the substance. Forensic chemists, for example, will measure the percentage composition of an unknown powder and compare it with the percentage compositions for sugar, salt, or cocaine to identify the powder. Calculating the percentage composition of any element in a substance is straightforward if the chemical formula is known. The calculation depends on the formula weight of the substance, the atomic weight of the element in interest, and the number of atoms of the element of the chemical formula. The percent composition of the element is the number of atoms in the element times the atomic weight of the element divided by the formula weight of the element times 100%.